Bien, on va démarrer. Donc, je suis évidemment ravi de pouvoir, pour une fois, présenter en vrai l'orateur, donc Francesco Zamponi, qui est un spécialiste de la physique statistique des systèmes désordonnés et qui a donc beaucoup travaillé en particulier sur la transition vitreuse, les problèmes d'empilement de sphères et de façon plus générale, du coup, justement, de ce qu'on appelle Constraint Satisfaction Problems, donc de problèmes où on a un certain nombre de contraintes à satisfaire, et vous verrez, donc on trouve une phénoménologie qui est très intéressante. Et mon intuition, c'est que ces problèmes de satisfaction de contraintes ont un grand avenir dans leur application à l'économie ou aux sciences sociales. Et donc il me semblait que c'était intéressant d'avoir une présentation de ces problèmes au sein de ce cours. Voilà. Merci Francesco.
Merci beaucoup Jean-Philippe pour l'invitation et merci d'être venu assister. Je suis content de donner un séminaire en pouvant regarder les visages des gens qui écoutent après beaucoup de temps. So okay, I will then switch to English and so I'm, as Jean-Philippe said, I'm a statistical physicist and I'm going to present a class of constraint satisfaction problems and in particular random constraint satisfaction problems. I will explain what I mean by this. Because these are problems that have been studied in detail by my community and also it's a kind of interdisciplinary subject where there has been a lot of exchange with mathematicians and computer scientists. And yes, with Jean-Philippe, we think that these are also potentially good models for some problems in economics. So we hope that maybe one day there will be some exchange also with the community of economists. So the plan for the talk is to first introduce constraint satisfaction problems and then explain why from the worst case scenario that is typical of the mathematical analysis of these problems, we can move to a more like statistical point of view. So I will introduce random constraint satisfaction problems, and I will show you that these problems exhibit interesting phase transitions and also very interesting dynamics. So when you try to find solutions with algorithms. And then I will conclude by introducing an agent-based model that we developed with Jean-Philippe to try to apply ideas coming from these problems to a kind of macroeconomic setting. Okay, so what are constraint satisfaction problems? I think the best is to give some examples. So a very famous one is the coloring problem. So you have Q colors. For example, here is 3, red, blue, and green. So you are given an instance of the problem. So an instance of the problem is a graph. So you have n nodes. So each point here is a node. And you have a certain number m of links that connect to two nodes. And so C here is the connectivity, is the average connectivity of one node. And the problem that you have to solve is that you have to assign a color to each node in such a way that there is no link that connects two nodes of the same color. Okay? So the constraints is that the links should connect nodes with different colors. And so in this formulation, this is what is called the decision problem. So given an instance, given a graph, the answer can be yes if there is a coloring, if there is a way to put the colors to satisfy the constraints, or no in the opposite case. There are also other variants of the other formulation of the problem. For example, I could ask you to count the number of possible colorings of a given graph, but I will focus today on the decision problem. And so just to fix the notations, I will say that a given instance, so a given graph, is satisfiable or sat if there is a coloring, so if there is a solution, or unsatisfiable or unsat if there is no solution to the constraints. So another problem of this kind on which I spent a lot of time is the problem of packing spheres. So in this case you are given n centers that are the positions of the spheres and that lie that stay in a cubic volume V, for example with periodic boundary conditions, and let me also introduce some tolerance parameter delta. And so then I will give you, as an instance of the problem, I will give you an initial configuration of the spheres, and of course the size of the spheres, sigma. And so the question is, can you find the configuration of the sphere centers that is not so far away from the initial one, so such that the mean square displacement between the initial configuration and the actual configuration that you find is bounded by this tolerance parameter, and no pair of spheres overlap. Okay, so in general, in the initial configuration there can be overlaps, and the question is, can you rearrange a little bit the spheres, but not moving too much, in such a way that there is no overlap. So the important parameter here is the packing fraction, which is the fraction of volume occupied by spheres when they don't overlap. So it's given by this formula. And I also would like to stress for later that if you take a sphere and you draw other spheres at random at a given packing fraction, then the average number of spheres that will overlap a given one is 8 times the packing fraction, and you can think to this as a kind of effective number of constraints per particle. So each particle at the beginning will on average overlap with 8 neighbors, and so you have to reorganize things locally around each particle in such a way that you eliminate these constraints. Okay, so this is a kind of the average connectivity of the initial configuration. Okay, the third problem I would like to give as an example is the so-called perceptron problem. So in this case you have a given instance is formulated in terms of m vectors. So you have m vectors that are called input. So you have these vectors y here. Sorry, here L should be n. So these are n-dimensional vectors, and to each vector is associated a label, sigma. You can think to sigma as 0 or 1, for example, or -1 and +1 in this formulation. So you divide the vectors in two classes. Some vectors have a label 1 and other vectors have a label -1. And what you want to do is to find a vector j such that you can classify the vectors in this way. So the label of a vector should be the sign of the scalar product of j with the vector. So if you want, you have these vectors that are organized in this n-dimensional space, and you have some vectors that are black and some vectors that are white, for example. So these are the two labels, and you want to find a hyperplane that separates the black vectors from the white vectors, for example. So an equivalent formulation of this problem, if you multiply here by sigma both sides, you see that you get 1 equal to sigma times the sign of j dot y, and so this amounts to say that the scalar product of j with the vector sigma y should be positive. So if you want, you can reformulate the problem in introducing what are called patterns, eta. So each pattern is sigma times y, and you want all these patterns to stay on the same side of the hyperplane. Okay, so you just mirror each of the negative, each of the y that correspond to a negative sigma. You reflect it on the other side, and then you want all of them to be on the same side. So this is perhaps the simplest example of what are called classification problems in machine learning, and these are problems that today are very much investigated. For example, you have images of dogs and cats, and you want to separate the dogs from the cats, and so it's essentially this kind of problem. So this is the simplest formulation. Today people use more complicated machines, if you want, but this is the simplest machine that is perhaps able to do this classification. Okay, so now I would like to introduce the notion of complexity classes. And before I do that, I would like you to note that there is a kind of common structure in all these problems. So here I have the three problems I introduced: the coloring problem, the sphere packing, and the perceptron. And so in all these cases, I have instances of the problem. So I have an ensemble of problems, and each, for example, in the coloring, each graph is a given instance of the problem. In the sphere packing case, the instance is the initial position of the spheres, and in the perceptron case, these are the patterns. And then the instances are characterized by a size that is going to be important. So in the case of the coloring, it is the number of vertices that you have. In the case of the packing of spheres, is the number of spheres that you have. And in the case of the perceptron, it is the dimension of space. Then you have some variables. These are the variables that you should adjust in order to find the solution to the constraints. And so for the coloring, it's the assignment of colors to the nodes. For the spheres is the position of the centers, and for the perceptron is this vector J of weights. And the last thing that is important is that instances naively can be classified by their difficulty. And this difficulty, intuitively, you expect that, for example, in the case of the graph coloring, the more you have links, the more it will be difficult to find a solution, right? And same in the case of the spheres. If they are bigger, it's going to be more difficult to pack them in a volume, because they will, at the beginning, there will be more overlaps, and then you have to do more work to eliminate these overlaps. And also in the case of the perceptron, the more you have patterns, and the more it's going to be difficult to classify them. So in all these cases, you have a parameter that is naturally the ratio of the number of constraints that you have divided by the number of variables. So m is the number of constraints and n is the number of variables. And this is a kind of intuitive measure of the difficulty of a given instance. I will make this more precise in a second. So the question that people are interested in is how difficult it is to find a solution algorithmically. And of course, you can always do brute force. So you can enumerate, for example, in the case of coloring, you have q to the power n possible configurations of the colors, because you have n vertices and you have q colors on each vertex. So you can just check all of them. And if you find a solution, you say, okay, my instance is satisfiable, and otherwise it is not satisfiable. So the problem is that this naturally takes a time that scales exponentially in n. Okay? So the question is, can we do something better than waiting an exponential time in the size of the instance? So the first thing that you want to do, then, if you want to do something better, is you want to be sure that if you are given the solution, you are able to check it in a time that is not exponential in n. And so this defines a class of problems that is called the NP class. And these are the problems that are easy to check. Okay, so if I give you the problem and the solution, you can check that the solution that I am giving you is a solution in a time that is not exponential in n. It's a polynomial of n. So typically it's linear in n. Okay, so this defines a class of problems that are, let's say, kind of treatable. I mean, if you have a solution, you can check that it is a solution. This is a kind of good requirement for a good problem. Of course, there are other classes that are more complicated, but I'm not going to discuss them. And so within this class, now you can define a class that is called P, and these are the problems that are easy to solve. So a problem is in P if, for any instance, you can find an algorithm that gives you the answer, satisfiable or not, and if it is satisfiable, also gives you the solution in time polynomial in n. Now it can be n or n square or n cube, depends on the problem, but not growing exponentially in n. Okay, and then people realized that they could introduce a class of interesting problems that are called NP-complete, and these are somehow the hardest problems in NP, and they are defined in this way. So a problem is is NP complete? Okay, first if it belongs to NP, and furthermore, if any instance of any other problem in NP can be mapped in polynomial time into an instance of A. So what does it mean? It means that if you are able to solve A in polynomial time, then you take any other problem in NP, you can map this problem into A in polynomial time, you can solve A in polynomial time, so you can solve your problem in polynomial time, okay? So if you want, this is a graphical representation of these sets of problems. So you have this class of NP problems that you can check easily, and within this class you have a subclass that are the easy problems, the problems that you can solve in polynomial time, and you have very hard problems that are the NP complete ones, and so if you can solve one of them, you can solve everything, I mean, all the problems in NP. So if you want, you have two possibilities. One possibility is that there is at least one NP complete problem that can be solved in polynomial time. So if you are able to do that, then you can solve all the NP problems in polynomial time. So P is equal to NP. Okay, the green set, it actually coincides with the full set of NP problems. The other possibility is that you can prove that there is at least one NP complete problem that cannot be solved in polynomial time. Actually, it's enough to prove it for one NP problem, not necessarily NP complete, but okay. In that case, P would be different from NP. This is an open problem, and it's listed as one of the most important problems in mathematics today. So if you are able to solve it, you can get $1 million prize. So, okay, so this is this construction of complexity classes that has been extended to many other kind of problems, and so there are many different complexity classes. Is a very beautiful construction. It was developed mostly in the 60s and 70s for at least for these things that I just explained. And but the important point that I would like to stress is that it is based on a worst case analysis, which means that these statements are supposed to be true for all instances of a given problem. And okay, I will come back to this point in a second, but I also want to stress that this analysis highlights the role of these specific problems that are the NP complete problem as the potentially most difficult in NP. I mean, if you are able to solve one of them, you are able to solve all the NP problems. The last thing I wanted to stress before I move to the second part is that you have seen from the examples that these kind of problems appear in many different areas of science. I introduced one problem of the problem of packing spheres is of course important for practical applications if you want to store oranges, but also it's very important in physics because it's related to the organization, for example, of atoms in solids. So if you want to study solid state physics, it's a very important problem. But I also mentioned the problem of the perceptron, which is a problem of machine learning, so it's relevant for inference and artificial intelligence and all kinds of applications, and also the problem of coloring. I mean, it originally comes from the problem of coloring maps, geographic maps, but it's also a problem that appears in many different contexts. So this class of problem is a very broad class that finds application in many different fields. Now, in the 80s, people found themselves in a kind of paradoxical situation because, as I told you, there was this theory of computational complexity, and there were many problems. For example, the coloring problems for all Q bigger than 3. These problems were proven to be NP complete. So there were probably NP complete problems. So these were supposed to be very hard. But on the other hand, people started to have good computers. And so they tried to, they naturally said, okay, let's take some instance of these problems. Let's try to solve them on a computer. And they introduced a series of simple algorithms that look for solutions of, for example, of a coloring problem, and they found that most instances could be solved very easily. So at some point, there was the question, where are the, I mean, we know that these problems are NP complete, so we know that, I mean, okay, I also forgot to say that nobody, I would say almost nobody expects P to be equal to NP, so most people, I would say, believe that there are problems that are really exponentially hard to solve. So people were convinced that, for example, the Q coloring for Q bigger than 3 takes exponential time to be solved in the worst case. But on the other hand, so there must be some graph that is difficult to solve. But when you try to construct a graph in practice, you often find that it's actually very easy to find if there is a coloring or not. So where are the really hard instances? And so this was the title of this first paper here. Where are the really hard instances? And so people said, okay, let's try to construct hard instances, also because they wanted to have benchmarks. And so they introduced this idea of random constraint satisfaction problems. So the motivation, I will explain what they are in a second, but so the motivation for to introduce random ensembles of constraint satisfaction problems was originally really as a practical way to construct difficult instances that could then be used as a benchmark for search algorithms. But okay, it has then been found that sometimes they can be even useful for applications. For example, if you want to test, if you want to test chips and things like that. But okay, the other interesting point for me in particular is that these problems, so random constraint satisfaction problems, turn out to be analytically tractable using methods from statistical physics, and this was kind of realized in a series of works in the early 80s. So even before these problems were used to construct hard instances, so there was a kind of convergence from the computer science community and the statistical physics community. So then, okay, how do we define these random constraint satisfaction problems? The idea is to construct an ensemble to introduce a probability distribution over the space of instances. So for example, in the case of coloring, you can introduce a probability distribution over the space of graphs, okay? So you can construct an ensemble of random graphs, and then you can ask the question, can I find a solution, can I find a coloring? What is the probability of that one of these graphs in my ensemble is as a coloring, as a solution? So the important point now is that you want, I mean, a good way of doing this is to introduce a probability distribution over instances with fixed difficulty. And I told you that intuitively the difficulty of an instance is the ratio of the number of constraints that you have divided by the number of variables that you have. So for example, in the case of the graph coloring, it's the connectivity, the average connectivity of the graph. So here I'm showing you an example taken from these two papers of a slightly different problem that I didn't introduce, but I'm not going to introduce it because I don't really need it. It's a set of constraints on Boolean variables, and it's called the K-SAT problem. Here we fix the alpha, which again is the kind of the average connectivity of a variable, so it's the number of constraints divided by the number of variables. And so you fix alpha, you take a probability distribution over the instances that have this fixed alpha, and then you can ask, so what they did in this paper was to measure numerically in the computer the probability that one instance in your ensemble for a given alpha, so this is alpha, is as a solution. Actually here it's 1 minus this, so it is the probability that there is no solution. But okay, you can flip the curve and you get the other one. And okay, what they observed is that if the number of variables is very small, so for example 12 here, then you have a very smooth curve that grows. Okay, of course this quantity grows when you increase alpha, because when you increase alpha you are adding more constraints. So if your problem was satisfiable before, maybe now it will not be satisfiable, but the inverse will not happen. Okay, so so this curve is a monotonically increasing curve. And so if you increase n now, what do you see? That it becomes sharper and sharper. So you really have the impression that if you fix alpha, for example, equal to 6, and you increase n, this probability will converge to 1. While if you fix alpha to 3, for example, and you increase n, it will converge to 0. And in between, there seems to be some very sharp increase that actually, when n goes to infinity, becomes a really discontinuous jump from 0 to 1. And this was shown in this paper by doing what statistical physicists do all the time, which is finite set scaling. So they, instead of plotting these curves as a function of alpha, they plotted the same curves, but as a function of a scaling variable y, which is alpha minus some critical value of alpha that they called alpha sat, which is around 4.2. Okay, it's more or less the point where these curves cross. And so this is a fitting parameter, if you want to. It's a parameter that you have to fix in this analysis. But so if you then multiply by some power of n, so in this way you are kind of zooming. When you increase n, you are zooming in the region around alpha sat, and so you see that you get a collapse of the curves. So this means that when n goes to infinity, these curves the probability as a function of y does not depend on n. So when you plot it as a function of alpha, it will be essentially a discontinuous jump from 0 to 1 when n is going to infinity. So, okay, this is done with relatively small sizes, but I think the collapse of the curves is really convincing, and later people proved the existence of this transition essentially, I mean, rigorously. So we are sure that there is this phase transition now. The other very interesting observation that was made in this series of works is that when you are near to this critical value alpha sat, where essentially the probability of finding a solution goes from 1 to 0, it also becomes very difficult to decide if an instance is satisfiable or not. So here what you have is a plot of the time you need to decide if your instance is satisfiable or not as a function of alpha for several values of n. And you see that, for example, when you increase the number of variables from 100 to 125, so it's just 25% increase, the time at the maximum goes from 400 to 1200, so it gets multiplied by a factor 3. And in fact, you can see, I mean, now it's well understood that the time seems to scale exponentially in the vicinity of this critical point. So if you want instances that are that have alpha bigger than alpha sat, so for example here with probability 1 they have no solution, and it's also very easy to show. The algorithms can show very easily that there is no solution. For example, if you run an algorithm, it will very easily find the contradiction between different constraints, and so it will tell you there is no solution. On the other hand, if alpha is smaller than alpha sat, with probability 1 you have a solution when n is large, and it's also easy to find. So the hard region is precisely the region close to the phase transition. So this gives you a concrete way to construct difficult instances, right? Because then you can fix alpha to be close to alpha sat, you can take n large, and you have a very difficult problem. So the time can become extremely large, and then if you have 1,000 or 10,000 variables, it will become essentially impossible to decide if there is a solution or not. Okay, so now I would like to spend a few minutes to rephrase these problems as problems in statistical physics, just to explain you how the methods of statistical physics can give insight on what's going on in the vicinity of this phase transition. So for example, in the case of the coloring problem, what you can do in the language of statistical physics is to introduce a variable on each vertex, which is a pot spin. So it takes values 1, 2, 3 up to q. Okay, so then each value corresponds to a color. Then again, one instance is a graph of nodes and links that connect the nodes. And then you can define an energy function or cost function. And the energy function, for a given configuration of the spins, you just define the energy as the sum over all the links. So here ij in brackets denotes one link, of a delta function that counts 1 if sigma is equal to sigma j and 0 otherwise. So this energy is just the number of links that are monochromatic, so that are not satisfied. Okay? So then, of course, if there is a solution, it means that there is a configuration of 0 energy. If there are no solutions, it means that the minimal energy is not 0, is positive. And now, given this energy function, you can compute what is called the partition function in statistical physics, which is just the sum over all possible configurations. So you have q to the n configurations of the exponential of minus beta h, where beta is a parameter that plays the role here of an inverse temperature. So this is the Boltzmann measure over configurations with this energy, and this is the associated partition function. And then we know from statistical physics that the ground state energy, or the lowest energy, is the limit of 0 temperature or infinite beta of this function. So now you have two possibilities. If the instance is satisfiable, then there is a coloring, and then the ground state energy, the minimal energy, is going to be 0. And if the minimal energy is 0, when beta is infinite, here you have e to the minus beta h is equal to 1 if the energy is 0, and it is equal to 0 otherwise. So this partition function is just the number of solutions that you have. Okay, so from this object you can reconstruct not only that there is a solution, but you can also count the number of solutions. Otherwise, if there is no coloring, then the ground state energy is positive, and the value of this quantity gives you the minimal number of monochromatic links that you can have in your problem. Now, I told you that it's interesting to introduce now a random ensemble of instances, and in the case of the coloring problem, the natural way of doing this is to introduce an ensemble of random graphs. So random graphs have been studied a lot in mathematics, and for example, a convenient ensemble of random graphs is the Erdos-Renyi ensemble, in which you just take all possible links. So you have n choose 2 links, and you just take m of them uniformly at random among all possible links. Okay, so this is a well-studied ensemble, and it has a very important property that is shared by most random graph ensembles. I mean, that have, let's say, that have a kind of bounded distribution of connectivities, if you want. I mean, unless you have a very broad distribution of connectivities, then these graphs will be locally tree-like, which means when the size of the graph goes to infinity at constant average connectivity, then if you look around one given variable, the graph will look like a tree, and the loops will be extremely long. So typically the length of the typical loops diverge as the logarithm of n. So this means that if you now remove a spin and you look to the neighbors of this spin when this spin is absent, then these neighbors are far away from each other because they are connected by loops that are very long. And then you can argue that since they are very far away, they are statistically uncorrelated. Okay, so if you consider the statistical measure, let's say the measure, I mean the Boltzmann measure over the set of configurations, and you look to the correlations in this Boltzmann measure, when you remove a spin, then when you remove a variable, then this variable here will be essentially uncorrelated from this variable here. And then you can, okay, so this is what is called in physics a mean field model. And so when people realized that these random constraint satisfaction problems had the kind of mean field network, then they started to use advanced mean field methods coming from statistical physics that were developed for disordered systems. And so, for example, you can check these two papers, but many others have been written more or less at the same time. And so, using these mean field statistical physics methods, they could compute exactly the partition function. So, more precisely, they could compute the average free energy over the ensemble of instances. But from this quantity, you can compute the ground state energy, so you can decide if the ground state energy is 0, then your instances will be satisfiable, otherwise they are unsatisfiable. You can count the number of solutions, or more precisely the entropy of solutions, and so on. So you can get a lot of information over on the problem. On typical instances, because there is an average here. So then you can ask the question of studying rare instances, and then it's a more difficult problem that can be studied, but I will not discuss it today. Okay, so let me give you a sample of results from this approach. So I think the first important result is that there are actually many phase transitions, not just one. So I showed you one phase transition, which is the transition at which, the transition that separates the regime where all instances are satisfiable in the thermodynamic limit. Thermodynamic limit is when n goes to infinity, from the regime where all instances, let's say, are unsatisfiable when n goes to infinity. But so there are many other phase transitions. So this SAT-unsat transition is here. Okay. So here I'm showing the example of the coloring problem. So the control parameter is the connectivity of the graph, the average connectivity of the graph. So here there will be this SAT-unsat transition. So when the connectivity is too large, there are no colorings, and when the connectivity is small enough, then there are colorings. And this kind of sketch here, so you have to think to this square as the space of all possible colorings, okay, the space of all possible configurations of the colors. So you have q to the n points in this box. So of course the topology of this space is not that of a cube, but okay, it's more complicated, but okay, it's just an illustration. And what I'm drawing here is each of these points is a solution, okay? So here there are no solutions, so it's all white, and here there are solutions. Now I will explain why some points now are black and some are green, but so let me now try to illustrate what happens when you start from low connectivity and you increase the connectivity. So at very low connectivity, you have a lot of solutions in typical cases, and they also form a cluster. So they are next to each other. So if you are in a solution and you, for example, you change the color on a site, you change it from red to blue, you can change a little bit the colors around it, and you will find another solution. Okay? So there are many solutions, they are close by, and they are connected by small rearrangements around, that are localized, if you want, in the graph. When you increase connectivity, you have a first phase transition here, where this big cluster of solution breaks into small clusters. So now you still have many solutions, but they are organized in a different way. So you have groups of solutions that are close, but you also have groups of solutions that are far away. Far away, I mean that if you want to move from one solution in this cluster to another solution in this other cluster, you have to change essentially all the colors of all the vertices. You cannot just go from here to here just by doing small changes. You cannot start by coloring here, change a color, rearrange a little bit, do it again, and so on. This is impossible. At some point, you need to change the color of essentially all the variables. Okay? But okay, still you have many solutions, and not only you have many solutions, you have also many clusters. So you have an exponential number of clusters. Each cluster contains an exponential number of solutions. So you can define an entropy of clusters and an entropy of solutions. But they are difficult. I mean, but you cannot move easily from one to the other. Then there is another phase transition called the condensation, at which you start to have only few clusters. So typically you have a finite number, 2, 3, 4, 5 clusters. Okay, and then at some point the clusters disappear. When they disappear, this is the Sat-and-Sat transition. And okay, there is a last transition I want to mention, which is called the rigidity transition. So the rigidity transition is, okay, you can define what are called frozen variables. So frozen variables are variables that take the same value in all solutions of a cluster. So for example, if you have a cluster here, this one, all the solutions of this cluster, for example, have a certain vertex that is red. Okay, and if you change this color from red to blue, you are going to move away from this cluster. Okay, so clusters that are in black here are clusters that contain rigid variables, frozen variables. Okay, so at low connectivity you have a coexistence of frozen and non-frozen clusters, but at some point there is a transition where all the clusters now have frozen variables. So you see that the reason why I'm discussing this is that frozen variables are very important, because if you make a mistake, so for example, if you're looking for a solution and there is one vertex that must be red in all the solutions of these clusters, if you fix it to blue by mistake, you are going to kill all this cluster of solutions, and you can imagine that when there are frozen variables, it becomes more difficult to find solutions. Okay, so it's still an open problem, but I think many people in the community believe that frozen variables are what are really responsible for the hardness of these problems in the vicinity of this Sat-and-Sat transition. Okay, I will briefly mention what happens when you look to the problem at finite temperature. So finite temperature means that instead of looking for solutions that are the ground states, so minimal energy value of this energy function, you give a weight e to the minus beta h to each configuration. So it means that you can tolerate some errors. You don't want to satisfy all the constraints exactly. You can allow some of the constraints to be unsatisfied with some probability, which is essentially exponential of minus the energy divided by t. So beta here is 1 over t, and t is what we call temperature, by analogy with the statistical physics. So at finite temperature, you have a phase diagram like this. So at 0 temperature, you have this sequence of transitions, and so they extend into lines. So you have a line in particular that is called the dynamical transition line, that extends from this clustering transition at 0 temperature. And so above this line, again, the space of accessible configuration is connected like this, and below this line it is broken into these clusters. And then you also have a condensation line, and and here you have the Sat-and-Sat transition. So why I mention this is that the reason I mention this is that there is a very nice theorem that has been proved now 15 years ago. They proved that for temperatures below this line, this dynamical transition line, local Monte Carlo algorithms take an exponential time to equilibrate, so they don't equilibrate in the thermodynamic limit. What are local Monte Carlo algorithms? These are algorithms that are very widely used in statistical physics and beyond, in which you try to sample configurations from the Boltzmann distribution by just making local moves. So for example, you change the color of one vertex from red to blue, and you accept the move with a certain probability that is chosen in such a way that you guarantee that at long times you will sample states with the correct Boltzmann weight. Okay. The problem is that above this line, the time it takes for this process to converge to equilibrium is finite, typically, while below this line, it is exponential in the size of the system. So if your system is big, it will never equilibrate. And this means that if you try to look for solutions, for example, by doing Monte Carlo, it will fail. So a very simple way to look for solutions using Monte Carlo is what is called simulated annealing. So you start from very high temperature. At very high temperature, the Boltzmann distribution is uniform over all colorings. So you start from a random configuration of colors, and then you start to do Monte Carlo sampling, and you decrease the temperature slowly, and you hope that when you arrive to 0 temperature, you will end up in a solution. So this is an algorithm that has been introduced in 1983, and it's now very, very popular. But this theorem tells you that this algorithm will not work in polynomial time above the dynamical transition. So if you are at a connectivity above this point CD, and you start at infinite temperature and you cool slowly your system, at this point you will fall out of equilibrium, and it will take an exponential time to follow the state of the system to 0 temperature and to find the solution. So at least this is a proof that one particular algorithm is going to take exponential time to find solutions above this value of connectivity. Okay? Now this does not mean that it's impossible to find solutions in this region. So you can there are other algorithms called, for example, you can look to Walk-Sat is a simple variant of simulated annealing that are able to find solutions in this regime. But then, I mean, the problem is that in this region, because there are all these clusters of solutions that are distributed in a very complicated way in the space of solutions, the way local algorithms will explore this space to find solution becomes very dependent on the details. And so some algorithms will fail and others will succeed. And so what typically happens is that there is a critical value of connectivity, Cj, let's say, where a given algorithm will start to fail, but this will depend on the algorithm. And the question is there some bound? For example, can we prove that no algorithm is able to succeed beyond a certain connectivity? And this is an open problem. And also, if you want, the origin of the hardness is still debated, and as I told you, some people think that it's due to frozen variables, some people think it's due to these clustered structures, and so on. So there is it's an ongoing subject of research. So the main message of this part is that so from statistical physics you can show that random constraint satisfaction problems generically have this structure, so they show these clusters of solutions in this clustering phenomenon in the space of solutions, and this has important consequences for your ability to find solutions, because local algorithms will typically try to find solution but will get stuck in some cluster, and then depending on the cluster it can contain a solution or not, and so the algorithm can succeed or fail, and this depends on the algorithm. There are cases, and I give you some examples, where you can analyze in detail the dynamics of some algorithms, not Monte Carlo, because Monte Carlo, as I told you, there is a theorem that shows that it will not work. But there are other algorithms that you can analyze, not rigorously. These are not theorems, but there are theoretical physics analysis. So we believe they are correct, but there are details of the mathematics that are not fixed. So there is no precise proof. But in these papers, you can find cases where you can really show that a given algorithm has a threshold in this connectivity where it will start to fail. Okay, now the last thing I wanted to mention is how can we apply these ideas to problems in economy. So before I do that, let me introduce a little generalization of the perceptron problem. So I told you the perceptron problem was the problem of I give you m vectors in n dimensions, and you have to find a vector j that is such that the scalar product of j with all these vectors is positive. So I want to find a hyperplane such that all vectors are on one side of this hyperplane. So this was for sigma equal to 0. Now let me generalize this by introducing a value sigma. So now I don't want the scalar product to be just positive. I want it to be bigger than some sigma. So okay, sigma equals 0 is the previous case. Sigma positive means that I want a more robust classification. So you can show that if you can satisfy this constraint, then the resulting classification is robust to noise. So if you now deform these patterns by a little bit of random noise, they will still be correctly classified. Okay, so this is a problem that was studied in a very famous paper by Elizabeth Garner, and it was a natural generalization of the perceptron to make the classification robust. But there is another thing that you can do, is to consider sigma negative. So if sigma is negative, then you are not classifying the patterns, because you also allow for a negative scalar product, but it's still a constraint satisfaction problem. You have to satisfy this constraint. And it has the interesting feature that it is non-convex. So you can show that in the problem for sigma positive and also for sigma equal to 0 is such that the space of solutions is convex. And so you cannot have this clustering phenomenon that I just introduced in the perceptron for positive sigma, but you can have it for negative sigma. Okay, so here is the phase diagram. This is sigma and this is alpha. Alpha is again the ratio of the number of patterns divided by the number of variables. So if sigma is positive and you increase alpha, it's very simple. You don't have all this clustering. You just go from here directly to here. Okay, so either you have a convex set of solutions that are connected, or you don't have solutions. But if you are at negative sigma, for example, sigma equal minus 2.5, you increase alpha and you go through all these transitions that I just introduced. So you have first the fragmentation of the space of solutions, and then the frozen variables and so on. So if you want to know the details, you can check this paper. And okay, so then we say sorry, I missed the slide. So okay, then there were some studies, in particular these two, that constructed models of the economy and of the ecology, so that these are kind of similar to the Lotka-Volterra, but with some different ingredients, and they turn out to be very similar to the perceptron. So we were a little bit motivated by this and by the idea that the perceptron constraint could look like a natural budget constraint for agents. So let me explain this. So suppose that you have agents and they trade some products, and so a given agent mu has a preference, if you want, psi mu for product I, and so if this is positive, then the agent wants to, so the agents, if you want, can either buy or sell these products, and so if psi is positive, they want to sell a quantity psi of the product, and if psi is negative, they want to buy a quantity psi of this product. So if pi is the price of product I, then the scalar product of psi mu with the vector p is the profit of the agent mu in a given round, provided that the agent is able to sell and buy the quantities that they want to sell or buy. Now, so if you want, then this constraint that the scalar product of the vector of preferences with the vector of prices must be bigger than something is a natural budget constraint. So your profit in a given round of transactions should be bigger than something. And also naturally this sigma can be negative or positive, because if it's positive you impose that the agent should make a profit, but maybe this is a bit too much to impose that at each round the agent should make a profit. So maybe you can allow the agents to borrow some money, so then sigma can be negative. But not, of course, the profit should not be too negative, otherwise it's a problem. So it's reasonable to think that this sigma can be negative, but maybe not too negative. So it's reasonable to impose this kind of constraint on agents. So this looks like a perceptron where you replace, so where psi play the role of the patterns, right? And the vector of prices plays the role of the vector j. Okay? So we thought with Jean-Philippe that maybe since this kind of constraint looks like a perceptron, and since we know that the perceptron for negative sigma has this interesting set of phase transitions and this interesting structure of the space of the solutions, maybe this could also be relevant for some problem in economy. There is an important difference because in the perceptron you consider the patterns as fixed, quenched, and you want to find a solution for the j given the patterns. But here in the economy, the preferences of the agents are clearly not fixed. They evolve in time. So if you want the patterns are evolving together with the prices. So there is the question whether this interesting structure of the space of solutions for the prices will persist if the disorder, if you want, if the patterns are evolving with time. So then we tried to construct a model to study this problem. So let me try to illustrate this model shortly. I will not go into all the details, but the idea is this: you have so you fix. So this h mu is the gap between the actual profit and the lower bound that you have on the profit. So you want this h to be positive. So you introduce again an energy function h, and the energy the energy associated to one agent is 0 if the agent is happy. So if the profit is bigger than sigma, and otherwise it is h squared. So this is a standard cost function that is used in the perceptron when it's used as a classifier. And we also impose that the average price should be 1 to fix the scale of money, and that the prices should be positive, of course. Okay, and then we can introduce the total supply and demand. So total supply is the sum of the positive psi, and the total demand is the sum of the negative psi. So there should be an absolute value here to make it positive. And then what we propose is, this is a rule that was inspired to the Mark 0 model that Jean-Philippe already introduced. We suppose that people look at the difference between supply and demand, and if, for example, supply is smaller than demand, and so if they are people who produce, okay, the suppliers, they look at the gap between supply and demand, and for example, if there is excess demand, they will increase their production, while if there is excess supply, they will reduce their production. On the other hand, the people who buy, they don't control the production, so what they do is they look at prices, and so if a given product is cheap, its price is smaller than the average, then they want to buy more, while if the product is expensive, they want to buy less. And so this is the rule that evolves the preferences. And now, given the preferences and the prices, so sorry, maybe I didn't say it, the prices are obtained by minimizing this energy function. So we try to make, the idea is that there is a kind of market that is able to set the prices, given the preferences, to set the prices in such a way that the constraints are as satisfied as possible. So the agents kind of coordinate in order to minimize the number of violated constraints, which of course can be debated if this is a good representation of the market, but this is just a model. Anyway, given the preferences and the prices, then transactions are performed, and we have to take into account the fact that there is no market clearing, if you want, so there is an excess supply or demand, so the agents have to readjust a little bit their preferences, and they do it proportionally to the availability of the products. And okay, we also introduce, to make the model, we realize that the model as such is unstable, so in order to make it stable, we had to introduce a production cost, so a kind of, I mean, whenever you produce something, you have to pay some cost, and this cost is then redistributed to the agents in form of wages. So it can be, you can think to it as either as a production cost that is used to pay for labor, or as a kind of tax that is imposed on production and then is redistributed as some benefit. Anyway, money is conserved, and the last thing is that if an agent is consistently below if the profit of an agent is consistently below the threshold sigma, the agent goes bankrupt and is replaced by a new agent. So we do this by an exponentially moving average of the last few steps in the dynamics. So I will show you, if I can take 5 minutes, I will show you a few results of the model with 100 products, 1,000 agents, and these parameters fixed to some value that are not very important. So if you change a little bit these parameters, the results will not change too much. So the important parameter is sigma. And so these are time series of the number of agents that are going to fail in a given step. So the number of agents that are not satisfied, okay, that have a profit below threshold. So you see, when sigma is large and positive, so if we impose to the agents that they should make a profit at each step, we have a lot of of failures, if you want, but it's a kind of smooth curve with small fluctuations, if you look to the scale here. Now, if you want, I will show this in better, but this is a regime where agents are failing all the time. They are replaced by new agents, and so there is no way to construct to have any emergent structure in the economy. It's not very interesting, if you want. Is a kind of strange state, if you want, this one. What is more interesting is when sigma is negative. So indeed, you allow the agents to be a little bit indebted in some cases, and so you have two regimes. So for when sigma is not too negative, you reach a kind of stationary state with fluctuations, and you have a small fraction of bankruptcies. So you see it's about 3%, so it's kind of reasonable. Here is 30% at each step, so you are removing 1/3 of the agents in each step. But when sigma is even smaller, you get an interesting regime where you have crisis. So you can see that most of the time there are no failures, but then sometimes there are spikes where you can replace up to 10% of the agents. And this is very similar to what we see in Mark 0, where you have this periodic crisis, and Jean-Philippe already explained. The mechanism here is, we could understand that it's very similar to the one in Mark 0, so the one that Jean-Philippe already explained. The other thing is that you can look to the curves of supply and demand versus price. So each point here is one product, and the color is just the density of points that you have. So you see that when sigma is large and positive, it's really a structureless phase where prices and preferences are completely random. So that's why I'm saying it's not very interesting. But when sigma is negative, you have a bimodal distribution of prices. This is the distribution of prices here. So you have the goods, the products spontaneously separate into cheap goods that have high demand and high supply, and expensive goods that have low demand and low supply. And and this is even more broad in the phase with crisis. So now the point is, there is this spontaneous separation of goods, but is it static or dynamic? And so for this you can look at the time series, for example, of a demand for these are free random goods, and you see that they don't stay all the time in the cheap or expensive sector. They switch. So a given product will switch from being expensive to being cheap at certain times, and will switch back at later times. And this happens in both phases, if you want, in the stable phase and also in the phase with crisis. But when you have crisis, you have that the cheap goods are, the demand for cheap goods is kind of exploding. The demand for expensive goods is going down, and then at some point there is a crisis and it's reset. But sometimes you have a switch. For example, here you see the blue one that was a cheap one, then it became expensive. So you still have switches, even if you have switches on top of crisis. While in the positive sigma case, you don't have anything interesting. I will maybe skip this. So in conclusion, so this is a simple model based on the perceptron. So it encodes these budget constraints on agents. And what we found that was kind of unexpected, because it was not built in the model, is that you have three phases. A phase with high debt, so when sigma is very negative, and then the economy is unstable because you can have these endogenous crises or cycles where you have that up to 10 or 15% of the agents can fail and the economy is kind of reset after that. If the debt is too low, so if you put a too high threshold, in particular positive sigma, then agents fail all the time and there is no structure in the economy and it's not very reasonable. So, but there is an intermediate level of sigma where you can get a stable economy that has very low bankruptcy rate and no aggregate level crisis, and also you have this spontaneous speciation, if you want, of goods where they separate into cheap and expensive ones, and with also spontaneous switches between the two that are interesting. And there is a mechanism for that is due to some random events that are then amplified by some feedback loops in the model that are discussed in the paper. So we don't think to this as a very realistic model, it's a toy model, but it's nice to find that, I mean, as you would expect, it's important to tune the level of debt that you want to allow in the economy to have something stable, and if sigma is too high or too low, you have instabilities. So we think to this as a kind of a first step towards using constraint satisfaction problem, I mean, to construct, let's say, agent-based models for the economy based on constraint satisfaction problems. And in particular, this model does not show multiple equilibria. We think that maybe there could be a way to make more complex models in such a way that you can have all this clustered structure of the space of prices that would then give you multiple solutions for the prices given the preferences, and then would give rise to complex dynamics where the prices could show big jumps and so on. So this is something that we are still trying to explore. And yes, this is my conclusion, so thank you very much.